Thank you for coming. This is going to be a serverless talk. And I know that most of the conference in these past 2 days has been around languages and deep coding and everything else. This is not going to be one of them. This is what I like to call an architectural session. That doesn't mean that I'm not going to do the demo. I'm going to show you some of the things. However, keep in mind that it's not going to be as low level as probably some of the Haskell talks or Ruby talks, or I don't know, some of those that you may be listening to for the past 2 days. Yeah, it's also the last talk, the last session of the day, the last session of the conference before the keynote, so feel free to enjoy it. I'm coming from Croatia. I'm actually joining you from Croatia. So I'm not living in the States, at least not yet. I'm traveling around the world, doing all sorts of different talks on the conferences, kind of consulting the top companies about using of cloud computing technologies, about AI, about some of the new stuff that's coming out. And I'm also I'm kind of run a company of 12 engineers. We are educators. We do these educational hackathons where we basically put 6 of you in a team, give you some challenge, some task, and give you the documentation where everything is written out, what you need to do, and then you need to do it. And we are not giving you typical lab instructions like step by step. We give you the problem, we give you the documentation, and we are there to support you, never answering your questions, just by asking more questions which are leading you towards the correct answer. So this is what I do. And what is serverless? I mean, probably each and every one of you already heard about it, and we are talking about serverless for, I think it's now been a decade since AWS Lambda. So basically, we are talking about abstractions. So anytime somebody new comes to the serverless talk, they're always expecting that it means that there are no servers. Everything is running somewhere. We don't have servers. We are probably running it on a bare metal processors, no servers, no operating system, nothing. Obviously, you guys know that that's not true. It's just that this technology abstracted the servers from us as end users, as coders. When we are writing the applications, we don't care about the server. We don't care about the CPU. We don't care about the memory. We don't care about infrastructure. We care about our business problem, which is basically the amounts of events that are going to come our way that we need to handle. We need to write the code, and we need to have a platform that's going to scale on its own. And basically, if we want to have this, we don't want to pay by CPU or by memory or by, I don't know, server. We want sub-second billing, which basically means I want to pay by the amount of requests I'm receiving or by the amount of times I'm running some function. I don't want to pay the CPU time because most of the time my CPU is doing nothing. So that's kind of an approach that serverless offered, and it's basically different because if you start thinking of serverless apps, you can't build a monolith in a serverless sense. Technically, in some platforms you can, but most of the time you can't. You are immediately in the decoupled microservices world. Immediately, when you start going serverless, you are into loosely coupled components. 2 functions that you deploy don't know anything about each other. You will need to connect them, and you will need to make them work together. They don't share anything between, only if you make them share through external libraries or something like that. But by definition, they're loosely coupled. On the other hand, in monoliths, we are used to kind of having memory, having all these fast operations inside of our servers because we have a server. In loosely coupled world, data is outside of client application. We'll always need to be pooling something somewhere, and that's how we are building the architecture. And basically, we are implementing micro-functionalities, which means that usually serverless function, as it is called, or serverless artifact, to be a little bit more abstract, is handling one job and one job only. So that basically means you have a function for writing something to the database, to that particular table, that particular object. You're not going to share that with writing to the database of something else. That might sound a little bit too much, a little bit above everything, but that's kind of what they had in mind when they were developing the framework. So obviously there are benefits, because if we are producing only small pieces of components, then they are actually easier by themselves. They're easier to maintain. We're actually better at writing them. We produce less bugs, so we ship code faster. We can make changes faster because we are upgrading each and every single piece. That's basically coming from the microservices world. Reduced DevOps, basically none. At least that's what we were promised. That we have a platform that's going to run and do this for us. We don't do anything except push our code to the central code repository. It's just going to trigger the deploy to the serverless platform. Nothing else. Maybe running some tests or whatever, but that's basically a developer job, not DevOps job. So we can always, I mean, you heard this probably a ton of times in the past 15 years. Whatever new thing comes in the tech world, whether it's cloud computing or containers or microservices or serverless or artificial intelligence or generative AI, it's always, we can focus on what's the most important. Every time they tell us, none of the time has it been true. There's always a ton of overwhelming, I would say, things that you need to take care before you can start focusing on your business logic. So that's basically what serverless is. And the idea of the technology itself is that we have events, and events can be anything, but it's always an event. It can be manually triggered click somewhere, or it can be a call to the API, or it can be change in some database. It can be file upload. It can be, I don't know, new message on the queue. Those are all events. Those events trigger functions which are written in basically any of the modern programming languages. I'm going to show you examples in Node.js, but that's just because it's the easiest thing to show starting up. But basically, you can use any of those. So we are writing functions, and guess what? We are not a single island. In those functions, we are using other cloud services. We need database. We need some kind of blob storage or object storage. We need maybe NoSQL storage. We need queues. We need caches. We need all those things, no matter what we are in the server, no matter that we are in the serverless world. So basically, event, whatever it is, triggers a function. Function talks to the services. At the end of the day, produces some result, either returning something back to us or doing something with the other server. And this is how they actually look like. There are two types of serverless workloads. And I'm talking about this for the last 3 or 4 years. When you talk with the vendors, they don't like it. When you come to Microsoft and tell them, basically, you have two serverless technologies. One is called Azure Functions. The other one is called Azure Logic Apps. They're going to tell you, no, we only have one serverless platform, and that's Azure Functions. Logic Apps are integration platform. No, they're not. They're serverless workflows which are done in a visual way. But they are still serverless, and you pay for them by the amount of executions. So by definition, they are serverless. So this is an example. On the left side is AWS Lambda, the first serverless technology that actually created all this fuss around. And on the right side is actually Logic Apps from Azure, from Microsoft. So we are kind of combining the processes of writing our own code and the processes of writing our own workloads. You will see, I will compare all of these, how they are called in each and every platform. But basically, Amazon also has its own workflow engine, which is called step functions. So there are many, many different options, but they are basically two types. One is writing your own code. The second one is using different elements to orchestrate that code. That's basically it. So this is an example coming from Google, but just to keep in mind, all those big three had some technology that became the starting point for serverless. That technology was actually called differently by each and every vendor, but behind it is the same exact thing, a managed VM which has a web server. Amazon calls this Elastic Beanstalk, Microsoft calls it Azure App Services, and Google calls it Google App Engine. It's exact same thing behind, managed VM. So 3 VMs put together, which take care of your code, which have a web server, which are exposing that web server to the outside world, and you can't connect to the actual VM, you can't update it because it's managed by them. Based on those, they produced their first versions of the serverless platforms. So that's actually what Google did. So they had a flexible runtime. Then on top of that, they had a standard write time, which they started to use Docker. Cloud Functions version 1 was really something you shouldn't be using at all. It wasn't working. It was a mess. Cloud Function version 2 actually does a lot of good work, and we can use it, and people are using it. However, keep in mind, this is going to be important later when I'm going to talk about a different approach to serverless. Keep in mind that Google Cloud Function version 2, what it actually does, it packs your code into a container and then runs it via Cloud Run, their container platform. So it is serverless. You are charged as it is serverless, but behind the scenes, they are building up Docker images and putting that to their own technology and actually exposing it like that. Why am I saying that that's important? Because you'll see that that's going to be the most common approach in a multi-cloud type of serverless world. So I mentioned some of the services which we need when we are going into the serverless world. We obviously need the database. I'm not going to be talking about the databases. That's kind of out of scope. However, we need to take care about some of the things which are crucial. I told you, those two functions that you deploy, they don't know anything about each other. So what you can do, which is a bad practice, is to actually make one of them talk directly to each other, to the other. And in that sense, you're going to leverage the HTTP protocol. Basically, you're going to talk between one another. And that's completely fine. But that doesn't scale. If you need to scale, then you're going to need some kind of messaging platform, messaging service, which is going to have what we nowadays call queues and topics. I'm going to explain each of them. But those are basically message brokers. Those message brokers can actually enable you to transfer one single piece of data from one function to the other in an actual scalable way. We'll see some of the patterns there. So basically, what's the difference first between intermediaries and brokers? Intermediaries are just translating what comes to them. So you can think about intermediaries as routers. So those are typical intermediaries. They receive something, they figure out where they need to push it, and they actually send it to that particular thing. In that sense, it makes a little difference between us directly calling the specific function or going through an intermediary. It can help with scalability because you can have multiple functions, so it can go round robin, for example. Typical load balancer scenario is intermediary. However, it still can happen that you are stuck with some amount of instances and that your message is going to get lost. Somebody will need to do repetition on the side of producer to be able to make sure that it's received on the other end. That's how intermediaries work. On the other hand, broker has a memory, usually a database. So broker can store any message it receives until it is able to push it to the receiver, and that receiver confirms that it actually receives it. So that's basically the difference. So push versus pull. In intermediaries, everything is in a push sense. So I'm talking to the intermediary, to the load balancer, for example. Then load balancer is talking to server, and it's how this thing actually works. In the broker world, sender is the one pushing. Actually, sender is the one sending the message. However, receiver needs to be pushing all the time, checking whether or not there's something for me there. If there is, please pass it over. And then the broker is going to be pushing the message. So that's the difference, and that's basically the combination. Ways to pull can vary depending on the scenario. It can be easy, receive and delete. So I'm a receiver, I take a message, and broker immediately deletes it because I said receive it, done. There's something which is called peak lock. Basically, peak lock means that I, as a receiver, I'm going to say, OK, I get the message, lock it, don't let anybody else read it. However, keep it until I tell you that I'm done with my job that I have to do about that message. So that's peak lock. Otherwise, in the first sense, what can happen in the first situation is that I receive a message. I start transacting that message. I start working with the message. I ran into an error for whatever reason, and that message is lost. If we use second scenario, we get the message, we work on it. If we do a correct job, we can tell our broker, all good, you can delete the message. But if we fail, somebody else can continue after a certain amount of time has passed. There's a timeout there. for the lock. So that's why the second option is better if you absolutely need that message to survive any kind of error on the receiver side. And there's a transactional model which is not doable in any other way except locally. So this is not that related to the serverless, but it's part of the ways to pool. That's why I have it there. So that basically means that we are pooling the message in a transaction. So we are approaching this topic like it is a transaction inside of the database. So until the message is done by the working with by the receiver, we are keeping the connection open. So until everything is done. And that's not doable when we are not inside of the same machine, inside of the same engine. So that's why we do it only locally. There are two entities that we are going to be using and two approaches. One of them are queues. You probably know about queues. So that's a sequential message log. First in, first out. So we are putting messages into the queue, and we have a receiver that's taking the message, doing some kind of work, and finishing off. So that's basically it. So we are sharing the cursors and logs over the log. Everything is going in a sequential sense. We have one producer, we have one receiver in this kind of situation. So that's a simple one. So when we just need to make sure that all of the messages are transacted, sent, stored, whatever the work that needs to be done is doing, the receiver is doing. However, we can achieve something else. We can achieve competing consumer scenario here. So what that means? That means that we can actually fill up our queue and have multiple receivers on the receiving end. Each one is taking one message and doing its own job, processing it, and storing it somewhere. This is a typical approach that's used in high-performance computing, for example, because you have this big amount of data which you need to process, so you're going to create lots of workers on the receiving end, each taking a piece and actually doing its own work. For that to be able to work correctly, you need a queue. That's why you are going to be setting up some kind of a queue. It's also good in the offline processing, basically because if, for whatever reason, if this is a situation when you're talking to some kind of a client machine or client device, that device might be offline. The message is stored in the queue until it's processed by the device that's been offline. Once the device gets online, it will actually process all the messages that were targeted to that particular device. Another option is topics. You can think of topics as n amount of queues which have all the same messages. So for example, we are going to create a topic for our SAP system. So we might have multiple producers on one end pushing stuff to that particular topic, and we might have multiple receivers. However, in this situation, each and every receiver is going to receive a copy of that particular message. Typical example that I like to share here is when you have a microservice-based web shop. And every little piece of your web shop is a separate service, which it would be in the serverless world. So your shopping cart is a separate service, your catalog is a separate service, your shipping is a separate service, your, I don't know, accounts, user accounts are separate service, your CRM is a separate, everything is separate. What happens? And it happens to Amazon all the time. It can happen that there is a change in the price. So what you need to do, you will need to change that price in your catalog. However, that catalog immediately needs to post to this particular topic that's used for changing the price, that the price has been changed. And each and every receiver, which can be your shopping cart, because people might have items in the shopping cart that need to be changed. It might be that you are changing all the prices all over the place, somewhere in the reports. That's another place where you need to change the price. Might be many other services. So each and every of those services needs to receive the copy of this message that the price has been changed. And for that, we are using topics. So basically, sender is the one who knows only about the topic. Receiver only knows about subscription. So basically, that's what we say. When I, as a shopping cart, need to receive details about price updates, I'm subscribing myself to that particular topic, which is called price change. In this particular situation, we have two topics. So we have one topic, but we have two types, basically two filters. So what's going to happen is that type order is going to go to the subscription 1, and type queue is going to go to the subscription 2, because those mechanisms usually have filters. So I can say, I'm a shopping cart, but I apply only for the price changes which have a tag need to update shopping cart. And that only is going to give me the price changes that I actually need to update. On the other hand, some other service is going to apply different kind of filter. And that's what the message broker is actually applying, and it's actually copying those messages and multiplying those messages. Typical example is actually Kafka. If you heard about Kafka, Apache Kafka, this is a typical example how Kafka works. There are other services, each and every cloud vendor has its own, but Kafka is probably the most popular open source variant. So why topics? Obviously, message distribution, partitioning, all those things that we need when we have a complex system, especially in a situation where we have this decoupled system like serverless. And the last but not the least thing that we need is actually API gateway. Because if you think about it, you're going to create hundreds of functions for your application, hundreds of different endpoints. There is no way that you are going to build a front end which have all those different little endpoints that are randomly named by the cloud provider. You will need an API gateway. You will need something that's going to orchestrate the traffic that's coming towards your serverless backend. API gateway basically gives you, this is an Amazon example, but it's the same thing with Google and Microsoft. So API gateway gives you the endpoint that's going to be your backend endpoint. You can version your endpoints. You have different staging and other environments, so basically production and staging environments. All sorts of different things that are important when you are changing stuff in your backend in the microservice world, in the serverless world, if you want. So this is what API gateway actually gives us. It also gives us throttling. So if we have some users that are not paying us enough to be using our platform each and every second or 20 times each second, then we can throttle those requests. So we can make them wait a little bit so that we don't spend as much of our resources on them. Because as I said, serverless is actually charged per run. So we don't want our customers who are not paying enough to be running the same as the ones that are paying premium. So we need something that's going to kind of make that differentiation. That's the API gateway. Caching is there. So we can cache some of the requests that we know are not changing that frequently. So authorization is there, all sorts of things. So you can create products, and basically that's the way that you can publish your backend and then have a front-end application on top of it, which is going to be running it. This is a really complex architecture, but not that complex at the end of the day. So we have some kind of clients. We have maybe CloudFront or maybe some other kind of web firewall. And we actually have an API gateway, which is talking to our endpoints in our serverless platform. In this case, this is AWS Lambda. An example of a serverless application. We will have API management layer, which is going to control all the HTTP routes. One of the routes is about posting a new invoice. So that HTTP call is going to trigger a function which knows what to do with the invoice. It's going to figure out what to do with the raw file. Probably first save it somewhere in the storage, then load it by the other function. It's going to convert it to JSON, and it's going to store it somewhere in some NoSQL database, for example. So that's going to be one function that does this part of the job. Second function is going to be one that's just fetching the invoice from the database. So it's going to fetch the JSON, format it in the sense that we need, and actually return it to the end user application, which is some kind of front end. This is done with the serverless components. There are many other use cases. Like IoT, that's a typical one. Obviously, we talked about microservices. Single-page application can leverage the backend done in serverless. Cloud automation, citizen developer. Maybe you didn't think about it, but there are many low-code, no-code platforms out there nowadays. And what's the best way to build a backend for them? Might be serverless. Might be the easiest thing. People don't talk about it that much, but if you think that you have a bunch of backend developers who can do really good backend, and you have a problem with front-end engineers, those front-end engineers might be able to be replaced with a low-code, no-code platform, just by designing the system and designing the user interface. It has been done, has not been done, depending on the enterprise that I've been working with, but some people are exploring that option. All right, let's now see how this whole thing looks like amongst different cloud vendors. So let me just use the slideshow. All right. So what I have here are all three clouds. So Google, AWS, and Azure. This is a typical function. As you can see, it's actually running on the Cloud Run. So it is a cloud function in Google, and it actually gives you automatically some of the metrics. I mean, you've probably seen some of the serverless platforms that are mostly reminding me, at least, each of the one another. So if I go to this particular endpoint, I can send a request, and it's actually replying my message. So I can change my message. And it's actually going to return that. So it's a really simple function, nothing special. That's why I'm saying it's not a deep demo. It's important because I'm going to show you the code of all of these functions, and you will be able to compare them and see where we have a problem. So these functions we can also always monitor the log. So as I said, it is a serverless technology, but we can see what's coming out. We just can't connect to the actual server that's running this workload. But we have a lot of different tools that we can use to actually monitor what's happening with our function. Same exact technology, same exact. Amazon's variant, the one that started it all, AWS Lambda. So again, Amazon portal, a little bit different. However, what Amazon did nowadays is they are not allowing you, they're allowing you can still create some of the typical Lambda functions, but usually they will force you to use the whole serverless stack, as they call it. So as you can see here, when I started this function, I immediately got API gateway, so API management deployed. I have an app platform. I have my function. So everything is pre-done correctly. All the IAM stuff in terms of security and control, it's all in place, even with the simplest demo, like I showed you on Google and like I'm going to show you now on AWS. So they are kind of building that in that particular sense. So you can manage immediately each and every of those little parts. So this is my app gateway. We can see the code of my function. So as you can see, again, it's really nothing that complex. I will show you the code in the Visual Studio Code in a minute. And if I go here, this is my endpoint. And again, I can say this is your message was test. I will again say hello from LambdaConf. And it's actually going to return that. So really simple, again, simple application. What you can see here is this part called prod. And what I can do, let me just copy the message. I can go to this part here and do the same exact thing. However, now I'm in the staging environment. So immediately when I deployed my first function in AWS, I got two environments because I'm using API management or API gateway in this sense. So API gateway is the one that created two environments and two deployments. So I now have two slots. I can first deploy to staging, figure out whether or not everything is working, and then switch to production. And last but not the least, Microsoft. So I have a function here. So I have a function app. That's how it's called in Microsoft's world. In that function app, I actually have two functions, which you can see at the bottom. Let me see if I can do something. It's here. So I have a hello function, and I have the other function. So I can now try to test my hello function. Let me just quickly grab the URL. OK, I have it open here. So this is the other function. Let me just copy it. So I have the URL. So my hello function is going to be here. and it has a message test. So it's a typical, the same way that I showed you in previous two approaches. So I can actually say, hello from LambdaConf, and that's what it's going to actually print out. The other function I have is actually taking my first and last name. Currently, it's printing null because it converted those to the lowercase. OK. If you don't want to do that, I will teach you how to do that. This is probably a bad thing to actually approach the query string with a whether or not it's capitalized or not. So this is another function. Why am I showing you this? You will see when I show you the code. Azure has a little bit different approach towards coding these things. So you can have multiple functions inside of the single source code. You can't do that with Google and Amazon. So those are some of the differences that come to mind immediately. So let's see now in Visual Studio Code basically how it all looks like. So this is a code in GCP. So we are using Google Cloud Functions. We are defining it like that. So you can see that functions.http, we are creating a new function basically and getting the message from the query, logging the message, returning the message. As I said, really simple thing. In AWS, the code looks like this. OK, I could have avoided logging more things so that we are not comparing apples and oranges. So it kind of reminds you, the JavaScript code is not that different. However, if you look at the header and all of these different things here, it's not the same. Let me open this one and open the Google one. And let's put them aside. So this is a Google implementation. Let's say we start from here. And this is Amazon's implementation. Similar, not same. And then when we come to Microsoft, then we have this option. Again, really similar, but not the same. And on the other hand, in Microsoft's world, we are defining multiple functions inside of a single file, not just inside of a single source code. You can't do that with either Amazon or Google. Why am I showing you this? Because the title of the talk is serverless the viable option for our multi-cloud strategy? And if you look at just this, the answer is probably not. And this is just the simple example and the simple source code. We already said that without other services, this is not going to work. So let's see what type of services do we need and how are they actually compared to each other in different cloud environments. So we're going to have AWS, Microsoft Azure, and GCP. And we have technologies and services for programming logic. So that's what we need. And the communication services, which I talked a little bit about queues, about topics, about gateways, and everything else. So even though when you see the JavaScript on my screen, it looks similar, the other technologies are not going to be as similar as the code is. So in AWS world, we talk about AWS Lambda. A lot of available languages. I mean, I probably haven't listed them all. So that's changing, and they're supporting more and more and more. Workflows are called AWS step functions. For queues, Amazon has its own implementations, which are called SNS and Simple Notification Service and Simple Queue Service. But they also support RabbitMQ with their Amazon MQ offering. Regarding Kafka, they have an actual implementation which is called Amazon Managed Streaming for Apache Kafka. It's a terrible name because it looks like it only supports the streaming part of the Kafka. But that's just the naming convention. It's a typical Kafka cluster that's managed by Amazon. For the gateway, they have an API gateway. We'll come to that. Microsoft functions are called Azure functions. A lot of available languages obviously out there, and workflows are done with logic apps. Keep in mind, both Amazon and Microsoft also have a durable option. So some of those functions can run indefinitely. So Microsoft calls this durable functions. So you can replicate some of the workflow functionalities in that kind of durable function scenarios. However, it's still a lot easier for most of the things to actually leverage logic apps as orchestrators between your separate functions. Microsoft supports queues and topics with its own Amazon Service Bus. So Microsoft Azure Service Bus. So it has queues and topics as types of brokers inside of that. It's a proprietary technology. It can be taught to use AMQP, but it doesn't like it that much. So just keep in mind, this is really proprietary, like SNS and SQS in Amazon. Microsoft does not support a managed Kafka cluster, but it actually supports the technology called Event Hubs, which has a Kafka API. So in most of the cases, your applications that are built for Kafka are going to work in the same manner just by using the API of the Event Hub for Kafka. Google calls its serverless platform the Cloud Functions. A lot of available languages. Workflow is workflow. That's how it's called. So you have functions and workflows, period. That's the Google serverless platform. Google has Cloud Pub Sub. That's their own proprietary topics and queues platform, which you can use for communication. You can see that each of the vendors here has really proprietary technologies. That's because it's not that easy to do these things. It's not that easy to guarantee that your message is actually going to get delivered. So they didn't want, in start, they didn't want to leave it to an open source project. They want everything under their control. So that, because they're not making a lot of money out of publish and subscribe messaging systems. They are making some, but it's not their main revenue generator in the cloud. Apache Kafka on Confluent Cloud is basically how Google supports Kafka. Confluent Cloud is Confluent is basically, you probably heard about them if you're working with Kafka. They're producing all sorts of different drivers and SDKs for Apache Kafka. And they're having their own Confluent Cloud running inside of Google's data center. So Google is partnering with them to actually enable you to use managed Kafka in Google. Regarding gateways, Amazon API Gateway, in Azure it is called Azure API Management. Google actually bought API-G, so they are integrating that into their platform, so it's still called API-G, API Management inside of the Google Cloud. So we still have 10 more minutes, but I can immediately ask you, so how does it look now? Is serverless a viable option for multi-cloud strategy? Doesn't look that good, because multi-cloud means that you can deploy to multiple clouds. Look at this map. You need to know a lot of different services. It might be that Kafka might sound like a good option, but then again, Amazon has a managed variant. Okay, I'm good there. I have one vendor that I rely on. Google has a managed variant, but it's done by the partner, so I have already two vendors. Microsoft doesn't even have a managed variant. It has something on its own, which might be good, might not. So there are so many different decisions that you need to make if you're going to go down the road of multi-cloud options in serverless world. Microsoft had an idea, and that idea was really viable. So what they had is they were looking at something which is called serverless framework. Serverless framework started as an idea that they would kind of abstract the way that you write the code, and then they would generate the different deployment mechanisms depending on the cloud that you are targeting. That's the philosophy. And this is what Microsoft still publishes on their own website. It's basically, okay, I'm going to leverage serverless framework inside of my deployment process. So I'm going to deploy the exact same serverless code one time to the Amazon, the second time to Azure. That was the idea. And then I have multi-cloud story in the serverless world. The problem is that the website of serverless framework today looks like this. Serverless apps on AWS Lambda. They still have a plugin. They still have a plugin which enables you to deploy to Azure. At least they say so. However, the last updated version of that plugin is 2022, which in cloud world is centuries. Second thing, I personally tried to make it work in the last 5 days. It doesn't work even with their examples. So it's not an option anymore. They tried, but they are now supporting AWS only. So they are basically that little framework that gives you a little more details in a sense and a little bit easier way to deploy AWS Lambda. You don't need to think about API management. You don't need to think about all of those different things that I said. They have those components. You just write it out and it deploys. But that's what Amazon is now working on with their CloudFormation. So I don't know. I don't see what's going to happen with these guys in the long run. However, there's another approach. And you might know from the brief history of the IT in the past 5 or 10 years that any time we approach to the cloud topic, to the topic of the cloud lock-in, the answer in avoiding lock-in were containers, was Kubernetes. It's probably going to be the same thing here. So what exists out there is that inside of our cluster, inside of our Kubernetes running on Amazon or Google or Azure, or maybe inside of our own data center, maybe DigitalOcean, maybe in Oracle, doesn't matter. Inside of that Kubernetes, we can actually spin up serverless platform on each and every node, probably. That serverless platform is basically an application that's running inside of the Kubernetes. And then we are running our functions as containers inside of our own cluster. And platform, serverless platform itself, provides us with all those different things that we need. For example, easier packaging of the function. They have bulletproof container images that are as little as possible so that our application spins up like this. It can scale out really quickly because of the Kubernetes platform. They give us all of that by deploying their code inside of our Kubernetes cluster. We are obviously going to pay them to do that, but that's how it actually works. And then we have an endpoint, and we have some kind of serverless command line interface. And that command line interface actually does a lot of work through the API endpoint, and then it actually deploys the new function where it makes sense. What ton of work does SLS CLI do? Basically, containerizes functions, because these are containers, as you can see, pushes to the registry, runs the tests, deploys, all sorts of different things. And you don't need to know Kubernetes to use this. I will show you in the demo. It's really a set of 2 commands that's required for you to deploy a new function. So any developer can do it. As long as you know how to write the code, you are good. This is not going to create a problem, because it's another level of abstraction on top of the Kubernetes service. One of them is actually called Open Function as a Service, OpenFaaS, basically. So that's one of the competitors in this world. And the other one is just right behind me, which is Golem Cloud. So those guys are actually trying to figure out how to make serverless inside of our own data center or inside of any cloud that we choose, and that we can actually run the same code base in each and every one of those clouds. So let me show you how it actually works, and then we are going to end our hanging out today. So basically, let me go here. So I showed you the serverless framework, and you can see this is their multi-cloud story 4 years ago, 5 years ago. 5 years ago. Crazy. In the cloud world, that really doesn't work. So this is my serverless platform running inside of my Kubernetes cluster. You can see that it has a local IP. That's because I've port forwarded my Kubernetes cluster to my machine so that I can show you the demo. So it has one function running, and it's running on this particular URL. So if I'm going to show it to you, I can actually invoke it from the system. And obviously, I'm missing something here, but I can actually take it here and paste it and just say message equals hello from LambdaConf. Here we go. So obviously, again, nothing special. I'm not trying to impress you, but my way of coding 10 different technologies is just a simple hello world. However, if we take a look, I will close those vendor technologies and open up our function as a service node application. So you can see it has some similarity to writing those in, for example, like Google. So it's really, really simple. This is everything that I needed to write for this to be working. So I just created a function, got the message from the query string, and actually put it back to the result and send that result back to the user. So what I could do now, I could do something like this. And I haven't tried this, so it might be interesting. I will change this to name. And I will say message hello, and then the name, and then let's add a space, then let's add last name, and that's going to be enough, I think. Good. So I need to send the name and the last name once I get this built. So how do I deploy this? As I said, as I promised, it's actually going to be pretty easy. Let me first do one thing. Let me prove that it's actually running on my Kubernetes cluster. So these are the functions that are running on the cluster inside of openfast.-fn namespace. And this is the actual platform up and running. And you can see that the platform consists of alerting system, the gateway, that's actually transferring the traffic. We have some nets, so internal network, basically. Prometheus is there for monitoring. And we have a queue that actually enables us to have the queue which we need between the functions. It's a simple platform. But it actually gives us enough to start doing some serverless work in the on-premises systems or in any of the cloud. So what I need to do now, I need to get this version built. If you want to explore this, that's really a nice thing to do. Keep in mind, if you're using silicon-based Mac, you need to use publish functionality and specify the platform. If you're using Intel, then you can use typical build and push. Otherwise, you need to use publish functionality. They don't tell you that in the tutorial. You need to figure that out yourself. So I'm going to publish this, which in a manner means that it's going to create a new container image for me, and it's actually going to push that container image to my Docker registry. Since I'm using the community edition, it's able only to do that with the public registries. It doesn't allow me. They want me to pay, obviously, to use private registries, but that's all right. So I created a new version of my container image, and I just need to deploy it. And if I just get my, okay, this is the new list, and we can get the pods, -fn, and you will see that I have a new version of my container running, which means new version of the function running. Now, let's see what happens here if I say name Tomislav and last name Tipuric. And it works. It's really good to do a live demo without testing it before. But it's a simple application. So that's the way that we can actually update our functions. And as you can see, it doesn't last that long. I mean, obviously, if you're going to be changing a lot of the things behind a function, adding new packages, for example, because this is a node-based application, so sometimes from time to time you're going to be adding new NPM packages, then maybe the process of building the container image and pushing it to the container registry is going to take a little bit longer. But usually, it's really, really, really fast. So it's quick. It can be used in any Kubernetes cluster. I'm running this in my Kubernetes cluster in Azure, but for the testing purposes, you can spin up a mini cube on your machine and actually get this thing up and running and try it out. Are there any questions? Yes.
If you could just repeat his question. Yeah, sure.
Okay, I can.
So I know some teams using serverless, and one of the things they're concerned with at the moment is FinOps or DevFinSecOps or whatever.
Okay,
but,
cost management.
Yeah,
okay,
yeah.
let's call it cost.
One of my friends summed it up, for every developer who leaves, we hire an accountant. Yeah. So can you take this kind of approach when you're trying to optimize for your spend and really fine-tune the environment so you're spending as little money as possible?
Okay, so the question is about FinOps, so basically cost management in the serverless world, and can we optimize for the cost? As you saw, if we are talking about sub-second billing, it's probably going to be the most complex thing in all of the cloud services world. Because to figure out the amount of stuff that's coming in and how much we are going to pay at the end of the month is something which is going to be 10 times harder than when we are talking about CPUs and memory, because those are kind of predictable. If they are running, you're paying. If they are not, you're not. In this sense, it's again true. However, we are paying so little by the requests, but those requests can come in any velocity, and then we might end up paying a lot. So it requires different math, and I would say that it requires a really good collaboration between the developer writing the code, somebody on the architectural point of view, some system architect or cloud architect, and the finance guys. They need to work together in a typical DevOps, FinOps framework situation. They need to work together to understand what's behind of this. So if you are going to use a typical serverless inside of any vendor. Other questions? Are you tired? Is it enough? All right. So to leave you with some of the thoughts on my end, basically, as you can see, serverless technologies are evolving rapidly. There are options in vendor world. There are options in open source world. So there are, serverless is probably the biggest cloud lock-in you can imagine. If you go with one vendor, it's going to be really problematic to get to the other vendor because you're used to so many of those different services. You can think about it in advance and actually try to figure out not to lock yourself in with some of the services, but it's really, really hard. Startups and open source community is very active here. At this moment, there are at least 10 serverless platforms out there that are trying to get some leverage amongst the top players that need to use those kinds of technologies. So look at it, think about it, try it out. My personal two favorites are the Golem Cloud and the FAS that I showed you. But there are others, there are other players there. Kubernetes has always been a key for avoiding the cloud lock-in. My personal opinion, it's again going to be the key in the serverless world. And with that, welcome to the serverless multi-cloud era. Thank you.